We talked about the relationship between heat and temperature when we defined heat. Heat is the transfer of energy to a system from a high temperature system to a low temperature system until those systems are in thermal equilibrium. Well, okay, so adding heat to an object changes its temperature. Removing heat from an object lowers, right? If heat goes from an object, the temperature lowers. So there's clearly a relationship between heat and temperature. So if I want to change the temperature of, say, a pot of water, a specific amount, say a specific temperature change, how much heat will I need? Well, that's an interesting question, right? Clearly heat, if you add heat, it will change the temperature, but how much heat is needed? Well, to do that, we have to define a term called heat capacity. The relationship between how much heat is added to an object and the temperature change of that object is actually very specifically dependent upon the material that you're heating. Water, to change water, say 1 Celsius degree, would require a different amount of heat than to change, let's say, carbon dioxide gas 1 Celsius degree, or wood 1 Celsius degree, or steel 1 Celsius degree. So different materials have very specific, what are called heat capacities. So heat capacity is just the relationship between heat and temperature change. Shown here is a capital C. It's the heat over the change in temperature of a material. It is dependent upon the material. So you can look up in large books what the heat capacity is for iron, gold, steel, water, ice, because ice actually has a different heat capacity for solid water than for liquid water, than for gaseous water. So heat capacity is how much heat do I need to add to that material to change it by 1 Celsius degree. There's a slight problem with heat capacity though. Heat capacity doesn't depend upon the quantity of material, and clearly that's an issue, right? It requires more heat to heat a large pot of boiling water than a small little tiny cup of water, right? It requires more heat to heat up a swimming pool full of water than a bathtub full of water. So it's not just the material that matters, but the amount of material, right? It takes twice as much heat to heat up twice as much water. The same temperature difference. So instead of heat capacity, which is shown here as a capital C, we quickly, in your book, quickly moves to talking about specific heat. That's a lowercase c here. Specific heat is it's a similar relationship you can see here, right? So this is for specific heat. But the only difference is we added a mass term in the denominator. So the specific heat is independent of the mass of the object. It just depends on the material itself. Whereas the heat capacity depends on not just the material, but the mass of that material as well. So rearranging this equation and solving for Q, the heat, we find that the heat needed is equal to the specific heat of the material. Again, it's material dependent, times the mass of that material. In this equation, it's SI, so it's kilograms, times the change in temperature that you want. And that kind of makes sense if you think about it, right? What 3 things are important when you want to change the temperature of an object? Well, it depends upon how much of a temperature change you want. Clearly, you have to add more heat if you want a bigger temperature change. It depends on the mass of the stuff you have, right? The more stuff you have, the more heat you need to get that same temperature change. And then finally, it depends on the material, because different materials are easier or harder to heat. Water, for instance, has a specific heat of 4,190 joules per kilogram per Kelvin. Or remember, Kelvin and Celsius degrees are the same scale. This is a delta T, so you can use Kelvin or you can use Celsius. It doesn't matter because the change in temperature for both units are the same. So it doesn't matter if it's joules per kilogram per Celsius degree or joules per kilogram per Kelvin. It takes 4,190 joules to heat 1 kilogram of water 1 Kelvin or 1 Celsius degree. A more common unit you're probably familiar with is the calorie. The calorie is defined as the amount of heat needed to raise 1 gram of water 1 degree Celsius. And that gram of water is at, I think, 25 degrees Celsius is the standard, because the heat capacity also depends slightly on temperature. But we're going to ignore that for now. Now that's the calorie. So calorie is a unit of heat. It's a unit of energy, right? It's a unit of heat. So the calorie, we think about that all the time. How many calories did I burn doing this exercise? How many calories does this food contain? Now the calories we use in our fitness apps and on food nutritional info, those are actually kilocalories, capital C calories. That's 1,000 times a normal calorie. So when you look on the treadmill and you burn 400 calories, wow, that's awesome. It's like, no, that's actually 400,000 normal calories. So this discussion is of heat capacity. So assuming no changes in phase, that you're heating water from some temperature to some other temperature, but it's still water, you can calculate what the heat needed is. Or if you're heating up a metal rod, or you're heating up the air in your house, whatever, as long as it's the same phase, you can calculate what the heat needed for a given temperature change using this equation here. What happens if the phase changes? What happens, how much heat is needed to melt ice? How much heat is needed to boil water? We'll get to that in just a moment.